Hey guys, Mr. Martin with a quick video over improper integrals. I'm going to split this into two videos. The first video will cover when we have infinity in our integrals, and the second video will cover when we have points of discontinuity within the integral. So to do an improper integral, we replace the infinity with either an A or a B. B if the infinity occurs as the upper limit, and A if the infinity occurs as the lower limit. Some of this is just us using basic number sense to evaluate the limit. If we get infinity or negative infinity as an answer, that's going to mean the limit does not exist, which would mean that the integral doesn't converge. And this topic of convergence will come back up when we do sequences and series. So in the first example, we are evaluating the integral from 1 to infinity of 1 over x dx. So now remember, a definite integral is meant to represent the area under a curve. So we're trying to figure out how much area is under the curve 1 over x if we go from 1 to infinity. So if we the first thing that we need to do is to put this in proper form. So this would be the limit as b approaches infinity. And we're using b because the infinity occurs as the upper limit. So the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. Besides that, everything else works out as we generally would expect. If we integrate 1 over x, we know that is the natural logarithm of x. So we would get the ln of x, improper notation. We would get the limit as b approaches infinity of the ln of x evaluated from 1 to b. So at this point, we would get the ln of b minus the ln of 1. And I keep forgetting the limit. It's, again, proper notation is to include the limit. So the ln of 1 is 0. So we know that this limit is, we know the ln is 0. But then if we look at the graph of y equals ln x, and we look at what happens when x goes out to infinity. When x goes to infinity, the y value is also going to go to infinity. So this is better seen if we look at the table, for instance. Quick shortcut is if you press plus, you can change how you increment the table. So we're going to go by thousands instead. So as x goes to infinity, our y value, it goes up much slower than x goes up, but it continues to go up. And if we change this to be, we'll go 20,000 so we can get back to 0. But then we go by like 1,000,000 instead. So even like y continues to go to infinity. It's unbounded, even though it goes very slowly. So that's going to mean that this doesn't converge. This goes to infinity at a very slow rate. So we end up with infinity minus 0, which is going to be infinity, which means that this limit does not exist. So this integral does not converge because it doesn't converge to a specific value. In example 2 is a similar kind of question where the first thing we want to do is rewrite this as the limit as b approaches infinity from 1 to b of e to the negative x dx. And so we know when we integrate e to some number multiplied by x, it evaluates to be e limit. It evaluates to be e to the same exponent divided by the number. So we're going to get e to the negative x divided by negative 1 evaluated from 1 to b. So if we continue, we're going to get the limit as b approaches infinity. So this is going to be -1. And then since the exponent is negative, we move it down to the bottom. And we're evaluating that from 1 to infinity. So e to the x is larger than -1. When e tends towards infinity, it's going to be, I don't know, -1 divided by some gigantic number. So the first part of this integral, when we, not infinity, this should be a b. When we substitute in b, this is going to converge to 0. So this first limit is going to be 0 because it's -1 divided by an eventually large number. And so that converges to 0. And so then when we substitute in 1, we get minus -1 over e to the first power, which is just going to be 1 over e. So again, if we look at the graph of y equals -1 divided by e to the x, I don't know why I put parentheses. I don't really need it. So you can see, if we zoom in, we'll say like right here, like really quickly, the graph converges to 0. Right around this point, we get a value that's close to 0. So when x gets out to infinity, this is going to be so close to 0, it's indistinguishable. So the first part, again, -1 over e to the eventually infinity, that's going to be 0. And so the last part is -1 over e to the first power. And this is how we get 1 over e. For example, 3, we have the infinity in our lower limit. We're going to have the limit as a approaches -infinity, e to the x over 4. X over 4 dx. Oh, man. Horrible notation. A to 0. So when we integrate, we're going to have e to the x over 4 and then divided by 1/4. So that's going to be times 4. And we also need to include our limit. And this is going from a to 0. So when we substitute in 0, we're going to have 4e to the 0 power, which is just going to be 4. And so then minus, let's just go ahead and assume that we get this -infinity. So minus 4e to the -infinity over 4. So since the exponent is negative, this is going to be equal to 4 minus 4 over e to the infinity over 4. And so again, you're going to have 4 divided by an eventually large number, which should converge to 0. So this is just going to be 4 minus 0, which equals 4. So this integral out to infinity or out to -infinity has an area that approaches 4. For the last example that we're going to do for this, we can also take this out and do this with volume. Let f of x be e to the -x, and r is the region in the first quadrant bounded between the graph of f and the x-axis, and we want to find the volume when we rotate this around the x-axis. So if we draw what e to the -x looks like, it's going to be handy to, I think we are. So if we have just e to the -x, it's just basically going to be the other graph turned around. So if we look at, we're looking at this region here rotated around the x-axis. So we're looking at basically when x is 0, we should get 1, and we'll put some other point out here, and it looks something like this. And we're taking this part and we're rotating it around the x-axis. So this is a setup for the washer method. Now again, this part never actually touches the x-axis. It gets really close to the x-axis. So we're rotating this around, the x-axis, and there's no hole in the graph. So this is going to be the disk method. So we know the volume for the disk method is pi times the integral from a to b of the radius squared dx. The radius is the distance from the x-axis to the curve. So from the x-axis to the curve is just y. The y value is e to the negative x. So our radius is e to the negative x. So our volume is going to be pi times the integral from 0 to, so this is unbounded, so our upper limit is going to be infinity, and we're going to have e to the, if I square e to the negative x, we get e to the negative 2x dx. And when we integrate this, all right, we're going to use bad notation. We're just going to pretend that we have the limits and stuff involved. It doesn't affect the answer. We're going to have pi times e to the negative 2x divided by negative 2. So we're going to put a negative and divide by 2, evaluated from 0 to infinity. So the same thing is, if we put it in, the first thing is that we get pi times negative 1 over 2e to the 2x. We could rewrite this from 0 to infinity. And so when x goes to infinity, the first part of this is going to convert, this is going to converge to 0. And so 0 times pi is going to be 0. So we get 0, and then minus what we get when we substitute in 0. So if you substitute in 0 for x, this is going to turn into a 1. And so we're just going to have minus negative pi over 2, which is just pi over 2. So the volume that this curve generates out to infinity is pi over 2. Again, because the first part of the integral converges to 0. So that concludes this video over improper integrals. So again, the integration itself is not going to be difficult. We just have to remember basic properties of limits. Constant divided by a large number is going to be 0. And if we end up with some sort of polynomial or trig function or something that goes out to infinity, we're probably going to end up with the does not exist. So in the second video, we'll cover what happens when we have an infinite limit as we approach a particular value. Thanks for watching.